Hi everybody, this is Cal with section 4.3, Some Extensions of the Limit Concept. In this section we're going to take the basic idea of the limit of a function as x approaches a cluster point C, and we're going to extend the ideas behind this limit to some other settings. Um, the first thing that we're going to go into is the idea of one-sided limits, how to approach C from the right or from the left. And the whole idea here is that we're just going to restrict, if I want x to come into C from the right, I'm just going to make the restriction that x has to be bigger than C, and then fold that into my previous definition of a limit. And if I want to do a left-hand limit at C, I'm going to make the restriction that x has to be less than C, and just fold that into my definition of the limit. And if you work through these definitions carefully, you can kind of see that this is what's happening. For instance, with the right-hand limit, instead of having 0 is less than the absolute value of x minus c is less than delta, we just have 0 is less than x minus c less than delta, because I want delta to be bigger than c. So that absolute value needs to be positive in the first place. Same kind of thing with this one. We have just c minus x instead of x minus c because I want x minus c to be negative. So c minus x should be positive. And you're familiar with one-sided limits, of course, from single variable calculus. And so this is just a slight modification of our limit definition. Theorem 432 provides the sequential version of one-sided limits, or rather for right-hand limits, and the book leaves the analogous result for left-hand limits to the reader. Theorem 433 is the result you're familiar with from Calc 1 about if the right-hand and left-hand limits make sense, then the overall limit as x approaches c of f is L if and only if the two one-sided limits exist and agree. And then 434 is examples, and you should work through these relatively carefully. Then we get into infinite limits, where the limit is plus or minus infinity. This is going to look a lot like what happens with properly divergent sequences. We say that f tends to infinity as x approaches c if for any alpha and r there exists a delta so that if x is delta close to c, then f is bigger than alpha. If I get close enough to c, then f is as large as I like. Similarly, for f tending to negative infinity, if x is close enough to c, then f gets as small as I like. And 436 gives examples, and again, this is analogous to properly divergent sequences from section 3.6. Paging forward, if it will let me, there we go. Let's see. Theorem 437 gives essentially a comparison theorem for limits that are equal to plus or minus infinity. And let's see. Definition 438 gives a one-sided limit as f goes to infinity. And this gives, just as f tends to, well, it's written for f tending to plus infinity, and as x comes into c from the right. And you can imagine what this definition should look like if this is a left-hand limit, if x comes in from the left. 439 gives examples. Finally, we have limits as x goes to infinity or negative infinity, and this should look a lot like sequential limits. Definition 4310 gives the definition of the limit as x goes to infinity of f. And 4311 gives the sequential version of that. And then 4312 gives examples. 4313 gives the limit as 4313 talks about f going to infinity as x goes to infinity. And this should look almost exactly like properly divergent sequences. And then, of course, 4314 gives the sequential version, and 4315 is something else. This is basically a ratio test for some limits involving infinity, which is nice. 4316 gives examples, and that's the section in a nutshell.